This is your equation number 1. Okay, so from here we can find the shear stress distribution. Okay, we can find the distribution of the shear stress in the flange. Okay, so we now know that shear xy of the flange. So this will be equal to Vy over Izz Qz multiplied by T, or divided by T of the flange. Right? So for this case, the thickness, right, the T of the flange, because of the shear force, is coming down in this direction. Right? In this direction is coming down. This is your Vy. So the perpendicular geometry is the what? Thickness, like what I told you before. Right? So we know that T flange, for this case, is equal to 0.16 meters. So finally, the rest is just plugging in formula, right? We calculated our Vy. So our Vy is equal to 90 times 10 power 3. Then divide by Izz, which is 5.813. 5.8133 times 10 to the power minus 6. Our Qz is 98 times 10 to the power minus 6 minus by 0.08 y squared. And then you divide by 0.16. So the outcome is this is equal to 9.4826 times 10 to the power minus 6 minus by 7.7409 times 10 to the power 9 y squared. Right. As good engineers, we have to find out, we need to know whether this is a right or this is the wrong answer. Can anyone tell me what test can you do to find out whether this answer is right or wrong, please? Anyone, please.
Plug in 0.
What do you mean plug in 0? Could you elaborate? You're not wrong, you're right.
So 0, it would have the maximum value. So in this case, we see we're always subtracting y squared. So when you plug in 0, it will be at its max.
Okay, you're partly right. The idea is there, but the explain it. Yeah. I'm not saying that you're wrong. You're right. Okay. Except with a slight error. If this is y, this is our shear, right? Because of how our structure is orientated, we don't know where the maximum is yet. We don't know the magnitude. However, we know that if at this end, right, I will, yeah, right. So this is one part of our curve that we formed. So this is where we have our shear xy at the flange. So the only way to check this is how?
Plug in y max and see if it's 0.
You don't know y max yet because y max is at the centroid. We are not at the centroid yet. So one way to do this is when shear xy is equal to 0, y must be equal to what? Right? So when you do this, y, okay, I've not tried yet. Okay, so it's equal to 9.4826 power of sorry, that is not -6, that is +6, my bad. Okay, power of 6, 9.4826 power of 6. Hey, turn on your calculator first. Divide by 7.7409 power of 9. Okay, then square root of my answer. So I get 0.035 or 34999. Right? Because at 0.035, right? At this point that I'm circling now, at this point I'm highlighting now, right? The shear stress has to be equal to 0. So if your equation is correct, when you let the expression be equal to 0, you should get y equal to 0.03499 meters. So this is valid. Am I clear? Yes or no? Okay. Right. So far it looks easy. Things are not so bad. Not the difficult. The confusion come is when we look at the web section. Okay. So I'm going to again copy this image. Right. So we're going to look into this diagram again. Right. So now we're finished with the flange. Next area of interest now. Right. So again, I'm going to sketch out. This is where my that is where my ZZ is. Okay. So this is where our ZZ is. And then we have our VY coming here. Right. So I'm going to call anything that is above the ZZ line for the web now. So we want to know what's on the web now. So I will call this top web section. Okay, so this part is my top web section. And the one below is the bottom web section. Okay. So I want to now what I'm interested now is I want to find the shear stress distribution in this area now. Top web section. Okay. Right. So we are going to I'm going to sketch this out again over here. Right. So this is what's of interest. Okay, so this is the flange. Now you still have to draw the flange. I'll explain to you why later. And then this is our top web section. Right, so this is our top web section now. And then again, we have our neutral axis or centroid. Okay. So now our y variable, again, our analysis has to start from the outside again. Okay. So we will have, this is where our line is going to stop. And the datum is at the ZZ line. So this is our y, right? And this is what we're going to find the equation. So this line over here, this is our y. And then over here, this is our vy. Okay. So this is our flange. And of this section over here, this is our web. Okay. So the top part is our flange. What I'm trying to highlight is this. When we are analyzing the web now, we have to include the area of the flange. We have to include the first moment area of the what? Flange. Okay. Why is that? Because the shear stress or the shear force Vy, right, will transmit from the what? Vy will transmit the shear stress from the flange to the web. Okay, right? That's why the analysis starts from where? It starts from outside coming in, analysis. I always emphasize that. The analysis starts from out. So the shear stress, the shear flow, okay, the shear flow will flow this way. Right? That's why last week we did, or not last week, on Tuesday, right? When we started this lecture, we got something known as what? Shear flow. Okay, can you see that? We have something known as shear flow. So from here, right, we have to start from the analysis will start from the max and come in. Okay, so that's why you have to include the area of the flange, the first moment of area of the flange. But the good news is this: the first moment area of the flange when analyzing the web, this is a what? Constant. Why this is a constant? And I'll write to you why. Okay, why this is a constant? Because now we're going to analyze the top web section, right? And the limit now is 0, y, and up to only 0.015 meters. Why? Because the distance from here to here, we know is 0.015. Okay, so whatever equation we have formed is going to be valid from there to 0.015 meters. Right? So our first moment of area now is equal to the Q, first moment of area, about the flange, plus by the first moment of area of the web. Okay, so again, we have applied one of the rules that says what? The analysis will start from what? Y max. Because it starts from Y max, where you go back in, okay, to reach your Y, we have to consider the area of your the region of the flange and how it will vary with your web slider. Okay, any questions so far? You okay?
Should we have Y and Y bar on the right hand side?
Oh yeah, I missed out the bar. Thank you. Okay.
Yeah, I have a question.
Yes.
So for the Q flange, is it now constant, or does it also have the Y variable?
It will be a
well?
constant now because the Y variable is not going to the flange, is it, right?
Right. Okay.
Yeah, getting it. You're seeing it. Good. Okay, you're seeing it. Good. Okay. So over here, the flange. So Q, the formula that I like to use is the width multiplied by depth divided by Y bar. Okay, so that's what I like to apply. So the width of the flange is 0.16. The depth is 0.02. The Y bar is equal to 0.035 minus by 0.01. Okay, why 0.035? So the distance from here to here, right? The distance from here to here is equal to 0.035, right? That's the maximum. And the distance from here to here, the individual centroid is 0.01. So that's why I minus 0.01. Okay. And the analysis again, the analysis datum is at the z-axis. Okay. So there's your area Y bar. So plus, so now we're going to consider the web. So the first one, we have two 2 over here means you have the left side, left and right web. Yes or no? Okay, left and right web. And then the width is equal to 0.02. And then the depth now is equal to 0.015 minus y. Okay, and then the center